As I said, my name is Wayne Scrivens. I'm the Product Support Manager for Sandvik Loading and Hauling. And today I'm going to talk about diesel engine technologies and the opportunities to reduce diesel exhaust emissions. Now, firstly, safety is the number one priority for us at Sandvik when we're designing our mining equipment, which means what we're introducing is the latest technology available to our equipment to reduce diesel exhaust emissions. Now let us look, firstly, diesel exhaust emissions comprise of both gaseous emissions and diesel particulate matter. So let us look at these different emissions in detail before we start looking at the technologies. Firstly, you have carbon monoxide. Now, CO is created when there is not enough oxygen present in the combustion chamber during the combustion of diesel fuel in a diesel engine. The CO is highly toxic and in very low concentrations, and at very high concentrations it can be lethal. And then you have nitrogen oxides, NOx, which consists of both nitrogen dioxide and nitric oxide. Now, nitrogen oxides are generated from the oxidation or burning of nitrogen, the most abundant gas in the atmosphere. It's typically formed when there is a very lean fuel-to-air ratio, a lot of oxygen content inside the combustion chamber, and also at very high temperatures. In particular, NO2 is highly toxic in low concentrations and can damage the lung tissue. Then you have carbon dioxide, CO2. Now this results in the oxidation or burning of the carbon in the fuel. Now because of CO2 production correlates very well with fuel consumption. And CO2, when breathed in by humans, can cause headaches, dizziness, and can be toxic at high enough concentrations. And then finally you have sulfur dioxide. Sulfur dioxide is formed from the burning of sulfur, which is present in the diesel fuel. It is highly toxic at very low concentrations and damages lung tissue. As it is breathed into the lungs, it reacts with moisture to form something like sulfuric acid. And then we have diesel particulate matter. The diesel particulate matter is formed from the incomplete combustion of diesel fuel in the combustion chamber. It was classified as a carcinogen by the World Health Organization in 2012, as it has been linked with lung cancer, respiratory problems, and heart disease. Underground miners are potentially exposed to much higher levels than other occupations. This is because there is less air underground to dilute these particulate matter emissions, and also they can get picked up by the ventilation system carried throughout the mine. Whereas on the surface, they would typically settle on the ground. So let us look at some of the ways to which we can reduce the exposure of miners to these emissions, whether they are gaseous emissions or diesel particulate matter. Firstly, one way to reduce exposure to diesel particulates is to use enclosed cabins and filtered air conditioning systems. Now, as standard on our cabins for our loading and hauling equipment, we use a Class 5 filter system to European standard EN 779. This filters 40 to 60% of particulates greater than 5 micron. The cabin is also pressurised to prevent the ingress of particulate matter and dust by any other means other than the air conditioning filter. The advantage of this is it controls the amount of dust and particulate matter that the operator is exposed to. but it doesn't prevent any exposure to miners outside the cabin. Another way to reduce exposure to exhaust emissions is to use low sulphur diesel fuels. Low sulphur diesel fuels reduces the formation of sulphur dioxide and also the formation of diesel particulate matter. When the sulphur burns in the combustion chamber, it can also get into the lubrication oil and down into the oil of the sump of the engine. What this then tends to do, it becomes acidic and it breaks down the lubrication properties of the oil. So this can then lead to more wear on the engine. So when you're using higher sulphur fuels, you need to change the oil interval so that you're changing the oil more regularly. The other thing is that new low emission Tier 4 engines require ultra low sulphur diesel fuel, as the sulphur dioxides that are produced from the burning of the sulphur poison the exhaust after treatment system. In order for us to introduce new engine technologies to lower emissions, many countries have now made ultra-low sulphur diesel fuel mandatory or compulsory. They have limited the amount of sulphur content that is allowed in the diesel. The maximum sulphur content for ultra-low sulphur diesel is between 10 to 15 parts per million of sulphur, which is equivalent to 15 milligrams per kilogram. Now what we show here is a map showing the maximum sulphur content that is allowed by different countries and laws around the world. Now you'll be able to see here that the ultra-low sulphur fuel in the light blue, it's been introduced to be able to introduce new diesel engine technologies in Europe, the United States, Japan, Korea and Australia. Now, ultra-low sulphur diesels may still be available in many of the other countries, but there is a risk that these fuels can become contaminated by higher sulphur fuels that are allowed through both storage and transportation. And this really is the biggest challenge for CIS countries, for us introducing new diesel engine technologies, as fuels with much higher sulphur content are still being used and are still allowed to be used. Exposure to diesel emissions can also be reduced by using low emission engines. In order to reduce off-road diesel emissions, the United States Environmental Protection Agency, the EPA, and the European Union, EU, introduced emission regulations in tiers or stages. These tiers or stages limit the maximum exhaust gas particulate matter emissions and gaseous emissions that can be produced by a diesel engine. Tier 1 began in 2000 for the engines that we use, and we have now moved to Tier 4 in 2014. The engine emissions are measured under an 8-mode cycle test for the certification, and then the weighted average emissions are calculated, and they need to fall in within the tier envelopes shown on this graph. You can see on this vertical column we have the maximum allowable diesel particulate matter. We have the maximum allowable NOx. So for Tier 1, the emissions of the engine has to fall within the green envelope. For Tier 3, within the orange, Tier 2 within the orange, Tier 3 within the red, and we come all the way down to Tier 4A, which is Tier 4 interim, and Tier 4B, commonly known as Tier 4 final. We can see from these results that the allowable particulate emissions has dropped by 90% when you go from Tier 3 to Tier 4 interim. And you also lower the NOx emissions by 40% when you go from Tier 3 to Tier 4 interim. And then when we go to Tier 4 final, we've seen a further 80% reduction in NOx compared to Tier 4 interim. Sandvik introduced the Tier 4 interim engine into our 5600 series loaders and trucks in 2011. We are now offering the Tier 4 final in 2014. The engines that we use are 13 litre and 16 litre engines from Volvo Penta that incorporate an SCR exhaust after-treatment system. SCR is the acronym for Selective Catalytic Reduction. And I'll go through how that system works in a little bit more detail. Firstly, the Volvo Tier 4 engine requires ultra-low sulphur diesel and a urea solution, commonly known as AdBlue. The AdBlue is put in a separate tank and a pump is used to inject it into the exhaust gas stream. The base engine is tuned with a very lean fuel-to-air ratio, which produces extremely high NOx, but a very, very low diesel particulate matter. But this also makes it very, very fuel efficient. The AdBlue is injected into the exhaust gas stream and it reacts with the NOx in the SCR catalytic converter. So basically you get a chemical reaction where the NOx emissions are oxidised to produce nitrogen, which as I said is the most abundant gas in the atmosphere, and H2O, water. Now this is very much proven technology as it has been around and used by Volvo in on-road trucks since 2007. The reason we like this solution is that unlike some other Tier 4 engines, there is no externally cooled gas circulation, EGR. Now this means that there's no additional cooling capacity required by our radiators to cool this exhaust gas that gets recirculated back into the engine. So we don't have to make our radiators bigger, we don't have to make our loaders and trucks larger, and we can still fit in the same tunnel space. The other thing to note with this solution is the base engine is very similar to a Tier 2 engine using the same technology. So it's very simple and easy to maintain because it's simple to what we already use now. So what we've done is, in the case of our LH517, we have combined our low emission Tier 4 engine with a loader designed for the optimum power to payload ratio and optimum power to weight ratio. The advantage of this combination we have seen is a significant reduction in fuel consumption. Our LH517 consumes up to 20% less fuel than our other competitors in the 17-tonne loader class. Now, as I said that fuel burn correlates with CO2 emissions, we are also lowering emissions, and we're lowering the CO2 that we produce. On top of that, we are seeing significant fuel savings, we're lowering operating costs, and potentially we could lower ventilation costs. So let's look at this in a little bit more detail. So we're almost 7 tonne lighter than other machines which carry the same payload. The advantage of this is that we can use an engine with much lower power, 285 kilowatts compared to over 230 kilowatts. In addition, we also use Tier 4 engines, which is extremely fuel efficient. It only consumes 216 grams per kilowatt hour compared to 224 or 226 for a Tier 3 engine. So as a result, our Tier 4 LH517 consumes 20% less fuel than our competitors. If we base our average duty cycle on 50% rated power, we are consuming 37 litres per hour compared to 45 in our competitors. If you then look at an average number of hours of 4,000 hours per operating year, we're saving about 32,000 litres of fuel per year. In this comparison, for a cost per litre of $1.35 Canadian dollars, that equates to approximately $43,200 per year. And we don't have access to ultra-low sulfur diesel, and we can't use Tier 4 engines. The next best option is to use a Tier 2 or 3 engine plus exhaust after-treatment systems. So let's go through what some of these different types of exhaust after-treatments are, and we'll explain to you how they work. Firstly, you have a diesel oxidation catalyst. And an oxidation catalyst oxidizes CO to CO2 emissions. As I said earlier, CO is highly toxic in very small concentrations, so it's desirable for us to oxidize the CO into CO2. Typically, an oxidation catalyst can reduce CO emissions by 80 to 90%. And this is now standard on all of our Sandvik loaders and trucks. It's fitted into the exhaust muffler. Another type of exhaust after-treatment system is the diesel particulate filter. Diesel particulate filters capture diesel particulates to prevent their release into the atmosphere. They typically replace the existing exhaust muffler. I'll go through some different types of diesel particulate filters in more detail. Firstly, there is the flow-through particulate filter. Now, it has a particle oxidation catalyst that can reduce particulate matter by 40 to 50%. The advantage of this system is that it flows through and cannot get blocked. It's more difficult to get blocked with diesel particulate matter or soot. The disadvantage is that it doesn't capture all of the soot and all of the diesel particulate matter. And then we have wall flow filters. Now, wall flow filters can trap up to 99% of diesel particulate matter. This trapped matter must be oxidized at very high temperatures or a filter will clog. So the diesel particulate matter is trapped in the filter, and you need to have high exhaust gas temperatures for it to burn off. Now, typically, exhaust gas temperature is elevated when an engine is working under very heavy load. But if the engine is not running under load for long periods of time, the exhaust temperature will not get hot enough to be able to burn off the trapped soot or diesel particulate matter. For very fast regeneration or burning off of the soot, the exhaust gas needs to be up close to 600 degrees Celsius. Unfortunately, most diesel engines do not have exhaust gas temperatures which get this hot. So what we need to do, as you can see in this graph, if the exhaust gas temperature is lower, we need to expose the diesel particulate matter to those high temperatures for longer periods of time, and the filter can become blocked. Even if your particulate filter is working correctly, not all of the diesel particulate matter can burn. So the particulate filter has to be regularly removed and cleaned, as it needs to remove the ash, which is incombustible. With a particulate filter, you need to understand the duty cycle of the machine and how it will operate. And if I give you an example for a truck underground, when it's fully loaded, travelling up a ramp, is under heavy load, and you have very high exhaust gas temperature. This is then burning off the soot that is captured in the particulate filter. And once we get to the surface and the loader is dumping, typically hydraulic systems don't pull as much load from an engine. So the exhaust gas is not as hot, but it's still developing diesel particulate matter that is trapped in the filter. Then when the truck turns around and it goes underground, once again, it is travelling back empty. It is not under a lot of load. The exhaust gas temperatures are not very hot. but it's still producing diesel particulate matter that is trapped in the filter. And then when we get underground, the truck is idling as it's waiting for the loader to load the box. Once again, it's a very cool exhaust gas temperature, but it's still generating diesel particulate matter. So we have to have that balance and ensure that the engine is under load for the right amount of time to be able to burn off the soot that is collected when the engine is not under load. So how do we prevent diesel particulate filters from becoming blocked if we can't get that really high exhaust gas temperature to be able to burn off the soot? One method is to use an oxidation catalyst in front of the diesel particulate filter. It basically converts NO to NO2, nitrogen dioxide. This nitrogen dioxide then oxidizes the trapped carbon inside the particulate filter. The advantage of this is that you're having a chemical reaction that can actually happen at a much lower exhaust gas temperature. You don't have to work the engine so hard all the time. The disadvantage of this method is it will increase NO2 emissions if there's not enough carbon actually trapped in the filter for it to have a chemical reaction. And as we said before, NO2 is highly toxic in low concentrations, so we need to ensure there's a right balance between generation of particulate matter and NO2 emissions. The other thing is this sort of solution requires ultra-low sulfur diesel fuel, because the creation of sulfur dioxide will react with the oxidation catalyst and poison the catalyst, making it ineffective. Another method for reducing filters from clogging and becoming blocked is to use what we call a fuel-borne catalyst. Basically, fuel additive is put into a separate tank and it is dosed into the fuel tank. It mixes with the fuel and it burns inside the combustion chamber. So it's very different to selective catalytic production. Now, as the additive burns in the combustion chamber, it adheres itself to the diesel particulate matter. When the diesel particulate matter is then trapped in the filter, it burns much faster at lower exhaust gas temperatures. In most cases, exhaust temperatures above 380 degrees Celsius for around 10% operating times will make this filter work correctly, which is quite achievable for a diesel engine. The other advantage of this type of solution is that diesel fuel with 50 to 500 parts per billion sulfur can be used in this system. So it makes this more suitable for countries without ultra-low sulfur diesel fuels. And this system is currently being developed by Sandvik for our big loaders and trucks. Another very important way to reduce the exposure of diesel exhaust emissions is to establish emissions-based maintenance. Engines must be routinely measured, engine emissions, should be routinely measured, and the engine should be repaired if the emissions start to increase. This also includes replacing dirty engines prior to them failing. Now, engine emissions can increase from a number of different factors, and I'll explain a few examples. Firstly, if an air filter or exhaust muffler becomes blocked, that can increase carbon monoxide emissions as well as the diesel particulate matter emissions. If injectors are worn or are faulty, then that also can increase either particulate matter or nitrogen oxide emissions. If the engine coolers become blocked and the engine overheats, not only does that reduce the life of the engine and cause wear, but it also can increase NO2 emissions and NOx emissions as the charger after coolers become blocked. And finally, contaminated fuel with water or dirt can wear components in the engine, and that will then increase exhaust emissions as well. Ventilation is another control that can be used to reduce the exposure to exhaust emissions. Ventilation is used to dilute gaseous emissions and particulate matter. Now, traditionally, many countries multiply the rated diesel power by a regulatory value to then give the minimum airflow requirement for one diesel engine. However, this method doesn't consider modern low emission engines, because with this method you would have the same ventilation rate for a Tier 4 engine compared to a non-tier engine. In reality, airflow requirements may be reduced by using a Tier 4 engine or a Tier 2, 3 engine with exhaust after-treatment systems. Here are some typical examples where the rated engine power is multiplied by a value, a regulatory value, to give the minimum airflow requirement. You can see here in New South Wales, Australia, we multiply 0.06 for our example of our LH517, which has a power of 285 kilowatts, and this requires 17.1 cubic metres per second of airflow, or this is equivalent to 36,233 cubic feet per minute. You can see that these values vary for different countries around the world, and from what I've seen for CIS countries, if you try to achieve 5 cubic metres per minute per horsepower for this particular engine, you would require 68,511 cubic feet per minute of airflow, which is very, very high. In Canada, the ventilation is calculated to dilute the gaseous emission to below what is called the threshold limit value. Now these TLV values are given on the right. So these are the maximum allowable values for emissions after they have been diluted by the ventilation. And you'll see that for nitrogen dioxide and sulfur dioxide, as I mentioned before, they need to be diluted to very low levels because they are highly toxic in low concentrations. The engines are tested in an 8-mode cycle test, similar to what the Environmental Protection Agency does, and the emissions are measured. The minimum ventilation is then calculated to dilute the worst gaseous emission that was measured. They then calculate an exhaust quality index from a combination of different gases and particulate matter emissions. We have CANMET certification for our Tier 4 engines in our LH517 loader. And the results of this testing show a 40% reduction in the ventilation requirement for this Tier 4 engine in our 517 compared to other 17-tonne loaders in this class. I'll show you the results. And you can also see that the LH517 Tier 4 engine requires 40% less ventilation compared to other competitors. In the US, the same 8-mode testing cycle is carried out and the ventilation is calculated to dilute the worst gas to their threshold limit values. And these values are also shown on the right-hand side of this slide. What EMSHA also do is they calculate the airflow required to dilute the particulate matter emissions down to 1.0 milligrams per cubic metre. This is then used as a guide for mining companies to select the cleanest engines that are available on the market. For the case of our LH517 with the Tier 4 instrument engine, the particulate index is 90% lower than its equivalent competitors, which I'll show you in the next slide. The EMSHA ventilation rate is shown on the left-hand side, and the EMSHA particulate index is shown on the right. The ventilation rate for the LH517 Tier 2 engine is governed by the worst emission, which is NOx. What you'll also notice is that the Tier 2 engine has a very similar ventilation rate to the Tier 3 engine. Now this is because we use a smaller engine with lower horsepower, because we require less horsepower because our machine is lighter to be able to provide the same performance. Now, a diesel engine without any exhaust after treatment cannot produce both low particulate matter and low NOx. There has to be a trade-off between the two. You have either high NOx, low particulate matter, or low NOx, high particulate matter. Now, our T2 engine has been tuned to produce slightly higher NOx, but still give a very good ventilation result compared to our competitors. But the advantage is the Tier 2 engine produces less smoke, diesel particulate matter, so it has a lower particulate index. And then you can see the Tier 4 interim engine. It is tuned for extremely high NOx and very, very low particulate matter, but it has the SCR after treatment system to then treat that NOx. So you can see that we have a 90% reduction in particulate matter emissions for a Tier 4 engine compared to other engines used in this loader class. While the actual ventilation requirements are actually governed by carbon dioxide emissions. Now remember we said that carbon dioxide production correlates with fuel burn. So what this means is we can't make this engine any cleaner and lower the emissions without reducing the amount of fuel that's consumed. As I said earlier, the minimum ventilation for our Tier 4 engine is governed by air required to dilute the CO2 emissions. Now, since CO2 emissions correlate with fuel burn, the best way to reduce that ventilation is to try to reduce fuel power, engine power, and fuel consumption. Now, this may be possible in the future using diesel-electric hybrids. Now, how a diesel-electric hybrid work are, a diesel engine runs at a constant speed and it drives a generator. This generator produces electricity which charges a battery on board the loader or truck, and then it drives electric wheel motors. Electric wheel motors can be used for braking the vehicle, and the energy that it's used can be stored in the battery, which can be then used later on during operation. This also, electric wheel drive motors and hybrids have much higher efficiency than our conventional torque converter and mechanical transmissions. So there is potential to be able to lower the required diesel power because it's a lot more energy efficient. And consequently, by lowering the size of the engine or the power required, we lower CO2 emissions and potentially further lower ventilation. So we can set the engine up to run at its optimum speed for very, very low fuel consumption. And because it's running at a constant speed, you almost eliminate any transient emissions, transient smoke or soot. And those of you who will know with the diesel engine, a turbocharged diesel engine in particular, when you accelerate a diesel engine from standing position, you get turbo lag, where fuel is injected into the combustion chamber. There is not enough air being produced by the turbo, and you get diesel particulate emissions until the turbocharger speeds up and provides enough air. By running at a constant speed, we are eliminating these transient smokes. And then, obviously, in the future, the best way to reduce diesel emissions is to actually eliminate diesel altogether and replace them with either battery or fuel cell power. The challenge with this technology is we need the battery to be small enough to be able to fit in the loader or truck and to be used underground, but it must be able to store enough energy for us to go through the loading and hauling process without having to recharge the battery too often. So what are the opportunities for reducing diesel exhaust emissions in CIS countries? Now we've discussed there are a number of methods for reducing the exposure of diesel exhaust emissions in CIS. We have enclosed cabins, we have Tier 2, Tier 3 engines, which can run on higher sulfur fuels. We have oxidation catalysts. We can provide good preventative emissions-based maintenance, good ventilation practices, and where possible, we can use electric loaders to eliminate diesels altogether. Today, we have Tier 4 engines available and different particular filter technologies. But in the future, ultra-low sulfur diesel fuel is really the most critical thing to introducing these new engine technologies into the CIS.